Last meeting, we ended with determining the number of stages. The sample problem that we used is giving you the procedure and how it's to be done graphically. And now we're going to, and also rather, it also taught you how to do it using Krimsker's equation. And during the dry lab, I give you two problems to process. One is on absorption, the other one is on stripping. And hopefully in that simple exercise, you're able to polish those things that I have discussed, apply the things that I have discussed during our synchronous meeting before the dry lab schedule. So for this afternoon and tonight, we will start with the determination of the minimum solvent requirement. How much liquid phase do you need for such recovery that is stated in the problem? Whether we're talking about gas absorption or stripping. So in the case of gas absorption, your liquid would be your solvent, and in the case of stripping, it would be your gas that will be your solvent. I have also discussed partly that the location of your operating line, if the process is gas absorption, should be above the equilibrium line or curve, whereas that of the stripping operating line will be below the equilibrium line or equilibrium curve. Now, what happens if we are to determine the minimum solvent requirement for gas absorption? So you have two illustrations here. One A is for gas absorption and B is for stripping. The original orientation of your operating line when we speak of gas absorption now was, shall I say, move in such a way that the end, which is y1, x1 here, was now made tangential to your equilibrium curve or line. Or simply put, let me just check. Or simply put, you projected your y1, x1 line here in the original orientation to this part of your curve. Now, at this point, we say that x1 is maximum, and that is the recovery of your liquid phase is maximized when we transfer this point here in the original orientation of your operating line for gas absorption in here. So that's how we do it when we determine the minimum solvent requirement for gas absorption. In the case of stripping, we also transfer the location of the end of the operating line. That's the upper end, in this case also the upper end. The upper end of the operating line upwards. So in here we do it sideways to the right, while in here we do it upwards. And in that manner, we are able to recover as much the biggest amount or the largest amount of solute in your gas phase, or that is your gas phase was able to take out the greatest amount of solute from the liquid phase in the case of stripping. So we transfer the original point here to a location that made the operating line for your stripping section tangential to your equilibrium line or curve. That's how we determine it, referring to the minimum solvent requirement. That's how it's done graphically. But this particular graphical interpretation of how we determine the minimum solvent requirement has to be translated to something that you can work on. And that's in the form of an equation. Now, so in terms of the pack tower design in gas absorption specifically, the recovery X1 is at a maximum when inert solvent flow rate is a minimum. What does this mean? We base our maximum recovery for our gas absorption process on the minimum solvent requirement that will achieve such maximum recovery. Actually, it's the same thing with stripping. We base the maximum recovery of our solvent gas based on its minimum requirements. So what would be the minimum amount of solvent gas that would be needed in the case of stripping that will maximize the recovery of a component in that gas, meaning the maximum amount of solute that could be taken out by your gas solvent from the liquid phase, that is. So this is the anchored principle, or the principle in which the minimum extraction of, let's say, a solute from the gas phase or a solute from the liquid phase is achieved in the process of gas absorption or stripping. Now, speaking of minimum solvent requirement, actually, we can already also determine the optimum solvent requirement from the minimum solvent requirement. That is based on what is given to us in our chemical engineer's handbook. So it's stated there that the actual liquid to gas ratio, that is the solvent circulation rate, normally will be greater than the minimum by as much as 25% to even 100%. Now, for optimization purposes, that is if we want to optimize the process, and that is always the case, optimization of the liquid to gas ratio in terms of total annual cost, now we consider the cost, often suggests that the molar liquid to gas ratio should be about 1.2 to 1.5 times the theoretical minimum. This is for gas absorption. But though this is specifically stated that this is the range for gas absorption, this same also we apply to stripping. What does this particular bullet here or thought is trying to tell us? That if you have already determined the minimum solvent requirement, whether that for gas absorption or that for stripping, in order for you to know the optimum solvent requirement, all you have to do is multiply it either by 1.2 to 1.5. In most cases, if you read books in unit operations, especially separation processes, they always maximize the optimum solvent requirement. So if you have already determined the minimum, you will have to multiply it by 1.5, and that would already be representing the optimum solvent requirement. So if the problem asks for the optimum solvent requirement, actually it already targets two information. It needs you to find the minimum solvent requirement in order for you to find the optimum solvent requirement. So in one question, actually, the problem already did ask you to represent your understanding and your learning on the minimum solvent requirement and the optimum solvent requirement. Now, as you could see here in stripping, it's the same case. So in our case, so as it would be uniform, we will follow what our sample problems in our unit operations book by John Kuplis and McCabe is using. So for optimum solvent requirement, you multiply the minimum solvent requirement that you were able to determine by 1.5. Now, here's a sample problem that will illustrate the use of the principle of the minimum solvent requirement, okay, in determining the optimum number of trays. So this is what I meant, that even though the problem is asking for something related to optimum operation or optimized operation, it need to go back to the minimum, because it's impossible to know the optimum if you do not know the minimum. So in this problem, a tray tower is absorbing ethyl alcohol from an inert gas stream using pure water at 303 Kelvin and 101.3 kilopascal. The inlet gas stream flow rate is 115 kilogram mole per hour, and it contains 3.3 mole percent alcohol. It is desired to recover 90% of the alcohol. The equilibrium relationship is y equal to 0.78x for the dilute stream. It's already dilute because you only have an original stream which is only containing 3.3 mole percent alcohol. Now, it is required here rather to determine the optimum number of trays needed. So for you to be able to know the optimum number of trays needed, of course, you need to know the optimum solvent requirement. If you know the optimum solvent requirement, or if you need to know the optimum solvent requirement, you need to know the minimum solvent requirement. So we do it backwards, just like what we do when we solve any problem. We present what is required, then what would be the formula to achieve the required, then we move towards the attainment of the required information. In this problem, our answer for the optimum number of trays needed is 4. But the question is, how did this 4 came about? So we will go now to the solution of this problem. Let's, for example, illustrate in a simple rectangular block the absorption tower. So your stream to be processed is in here, introduced at the bottom. The solvent is introduced on top. The solvent is pure. Solvent doesn't contain any component other than the solvent water. And your recovery is 90%. Notice that I have now labeled your column in two manners of labeling. The streams are labeled based on John Copley's labeling, but I've labeled the bottom as 1 and the top as 2 based on McCabe. The labeling 1 and 2 here is very beneficial or make things easy when we later on use the component balance equation in which we're using the inert streams and also in using the Crimser equation. I'm just placing it here that way you'll get used always that get used to the idea of seeing both representations here. That way you'll not be confused. Now, if we will start with the material balance, then we have to start with the overall material balance. We have to equate the sum of the phases that is entering our equipment. In this case, that would be LO and B sub n plus 1. And then we need to equate that to the sum of the living phases. That's the overall material balance. And that would represent our bulk phase M. From this particular overall material balance, we write down our component balance. And from here, we can write right away the alternative component balance using the inert streams L prime and V prime. And together with these two, the mole ratio rather than the mole fraction. Still balancing based on component A, just like what you have here in equation 2. Now, having written the three equations that we can work on, now we start with writing the values on equation 1. So if we write the values on equation 1, that would be LO. We're not given the original. In this case, that would be 2.20 plus 115 weight class. I will need to stop sharing for now because there is this block that keeps on popping here. I'll just pause for a while the recording. Okay, so this is your overall material balance equation. I missed to write the 2.2 for the solvent, but nonetheless, it's written here from equation 2 that our solvent is 2.20. It doesn't contain any of the solute. Our gas feed, the mixture is 115, and A in this particular mixture is 0.033. I think this is the ethyl alcohol, the 3.3 mole percent ethyl alcohol. Now, on the right side of this equation, we don't have anything known. So all 4 is unknown. So we need to consider using the third equation that was shown here. This third equation, because we have everything in here unknown. So we will do that in here. So before we can use equation 3, we need to determine the inert part of our phases. So for our solvent, the inert part would simply be the LO itself because it doesn't contain anything other than the solvent itself. So it's pure solvent. In the case of our gas mixture, that would be the original amount, and we need to multiply it to the mole fraction of the inert part of that particular mixture, which is, of course, the other part other than the solute. So that would be 1 minus y sub a n plus 1, giving us 111.21 in that case. So we multiply the 115 for the V sub n plus 1 to 1 minus 0.033 in here. That would give us 111.21. Now, these are already representing the L prime and the V prime. Now, then we need to determine the corresponding amounts of this XA1 and YA1. Now, for us to know that, we need to know the unrecovered ethyl alcohol. So the unrecovered ethyl alcohol will be the 10% of the original ethyl alcohol present in our mixture. So that would be the amount of the mixture multiplied to the percentage of ethyl alcohol to that times 10%, or that's 0.10. So this is the unrecovered ethyl alcohol. This unrecovered ethyl alcohol will be the same amount that would leave together with the inert part of your gas mixture because it's unrecovered. So the total amount of vapor leaving your absorption tower containing with it the unrecovered ethyl alcohol will be the 0.3795 plus this 111.21, and that would be 111.5895. If you know this total amount, then you can already determine the Y1, and that's the YA1 in here. So your YA1 is equal to the unrecovered, which is 0.3795 divided by this total amount, which is 111.5895, giving you, by the way, class, this is YA1. I missed to write the A here. So this is YA1, the YA1 that you have here. But actually, it's understood to be in terms of A because we're balancing everything here in terms of ethyl alcohol, which is A. So in this case, now we know already the YA1. So the next thing that we need to determine is the XA1 if possible. But if not, we will express XA1 in terms of YA1. So in this case, since optimum number of trays is based on minimum solvent requirement, we solve first for the minimum solvent requirement, L minimum prime. So when we solve the L minimum prime, that would be based on this particular component balance equation based on the inert amount of streams. But take note, class, that what you are determining is just the L prime minimum, not the, shall we say, the true L. But anyway, in this case, our L prime is just the L in this case because we don't have anything in our solvent. So based on the Y sub n maximum. Now, the problem gives us this equilibrium relationship at the start. So YAN plus 1 is equal to 0.78 X sub n MAX, or that would be the X sub n maximum. Now, in order for us to know the Xn minimum, then we need to use this particular equation here. Y1, or that would be YA1 divided by 0.78, I transfer the 0.78 here, will give us an Xn maximum of 0.0423. What does this particular value is telling you? That when you use this minimum amount of solvent, this is the maximum recovery. A representation of the maximum recovery of ethyl alcohol based on the concentration of ethyl alcohol in the solvent that leaves your column. So this X sub n maximum that we have solved based on the equilibrium equation will be the one that we will substitute in here in our, where is that? In our, this one, in the original equation for component balance using inert streams. So you need to determine the X sub n maximum and place it in here. That way you can solve for the minimum solvent requirement. And that's what's done in here. So everything was placed in here. These two are given. This is given. This one was solved. This one. And the X sub n was taken in the equilibrium relationship, or was taken from the equilibrium equation. Now, this is your minimum solvent requirement. Now, the problem is asking for the optimum number of stages. That way, we need to solve for the L optimum. So our L optimum is 1.5 times the L minimum. So what we do, we multiply this by 1.5, giving us 115.92. Now, using this value of the L optimum in lieu, or in lieu of the L prime minimum here, will lead us to determine the actual X sub n. The actual X sub n that will leave the column. Remember, class, that this X sub n is a representation of the concentration of the maximum amount of ethyl alcohol that your solvent water was able to recover. Now, if we increase, and this particular mole fraction is based on this minimum solvent. Now, what happens if you want to optimize? So we increase the number of solvent. So naturally, your X sub n will not be like this because you increase the amount of solvent that you use to 50% that of the minimum. So that's the purpose now of actually solving for the X sub n. The actual X sub n based on optimum condition already, wherein you're using 115.92 kilomole per hour of your solvent. So in this case, now you were able to determine the X sub n, which is 0.0286. This X sub n class is based on optimum condition already, while this one is based on minimum solvent requirement. This one is based on optimum solvent usage. Now, if this is already your X sub n, you need to determine the Ln in this case. What's the Ln? If you recall that your L prime optimum is your actual Ln, times 1 minus xn, then you will be able to determine the ln here, which is ano. This particular denominator here, which is 1 minus x sub n, actually came from what is written on the left side. So we just want to isolate the ln here to give us the actual ln in this case, which is 119.33. Now, I want to just, you may be wondering why we already have the L optim. Hello? Hello? Can you please mute yourselves? Thank you. Now, you may wonder why solve for that means the L sub n. You already solve for the L prime optimum and then you solve here for the Ln. Remember class that this L prime optimum is the optimum solvent that entered your column. This Ln is the solvent that left your column carrying with it this particular amount of ethyl alcohol. So we need to determine this Ln based on the L prime optimum. This one entered your column, while this one is the phase that left your column, carrying already this concentration of ethyl alcohol. Now, you know already the Ln, you have already the L prime optimum, which is 115.92, and you have the V. We did not change any of the V because that's the V that we processed, and it is summarized in here. So the V that was processed is 115, and the V1 was solved based on what was processed. And this LO is the L prime optimum, this one. And your Ln is the solvent that left your column carrying with it the ethyl alcohol already. This two is not changed, as I've said, because this one is, these two phases is not dependent on the solvent that is being required. Having these four phases now allows you to solve the two absorption factor. If you recall in our discussion last meeting, the absorption factor has to be determined for the top and the bottom part of your column to ensure that you're not assuming that your operating lines are straight. In this case, more or less, your operating lines are straight because the first two decimal values here are equal, but actually it's not really that straight. So we took the geometric mean, and this is the geometric mean. And the rest is just a substitution to the Krimser equation for determining the theoretical number of stages. So we use the same equation in determining the optimum number of stages, but this time you're using the streams that are already optimized. This one is already the optimum solvent requirement based on the minimum. This one is already the solvent carrying with it, or specifically the optimum solvent carrying with it the recovered ethyl alcohol. So this now represents then the optimum number of stages. So this is for our sample problem number 8, showing to you how to determine the optimum number of trays needed for a tray tower, or specifically for a tray absorption tower. Okay, so now we go to the pack tower. So your sample problem is expressed in terms of the tray tower. So now we can also have pack towers in the case of gas absorption. And of course, from the name of the tower itself, it contains packing materials. So inlet gas here, liquid outlet, liquid inlet, and you have the gas outlet here on top. So that's a specific example of a pack tower. Now, your pack tower have inside what we call packing materials, and these are examples of the different types of packing material. The purpose is to ensure that there will be intimate contact between the solvent and your feed gas. That way, the solvent is able to recover the content in the gas mixture that needs to be recovered. Okay. Another type of packing material is the structured packing material, and I have a few here: the flex ceramics, the Melapacks, the flexipacks, and the Munts structured packing material. Though you can read in literatures that the random packing materials are preferred over the random packing are preferred over the structured packing materials. So I would like to show to you a video about how a particular pack bed absorption tower works. So hopefully you can hear the, oh, sorry guys, sound. How come? As pause share, pause recording class. Wait.